Okay, so we are doing computations today. Right? So I'm addressing the issue of how you should compute things by hand. Right? And of course, you're welcome to look at the textbook and read and study and practice how they suggest doing it by hand. I'm just suggesting ways that are simpler in the sense that I'm trying to minimize the amount of memorization for you. Because a few questions there in the textbook suggest you take this, you apply this reduction formula. And they have a list of like 16 reduction formulas for the integrals. And I seriously doubt you want to memorize the whole list of all the formulas and then remember which one to apply. So I'm trying to get rid of those reduction formulas so that you don't have to remember those. Well, of course, you have to remember something. But I will specify exactly, precisely, what is it that you have to remember. And those are going to be simple trigonometric identities. And I have minimized the amount of those for the purpose of integrations. And what else? Well, the rules. Well, you have to remember some rules to apply. And then I will mention one trick that will not become a trick next class when I explain how to do some manipulations with formulas. But it's coming later. For today it will be a trick, but I'll say explicitly what that is. So the topic for today is going to be trigonometric integrals. And I'm not going to talk about all kind of possible trigonometric integrals that you may ever see in life. I will talk about specific trigonometric integrals, and those are exactly the ones you will see on the homework and on the test. And trigonometric integrals means those integrals where integrand has trigonometric functions involved, and those are going to be simple functions like sine and cosine, and those are going to be multiplied. So that's the basic thing, and I will only talk about indefinite integrals. Because once you learn how to take indefinite, you can take definite. So I look at integrals like cosine to some power of the argument 3x minus 2 multiplied by sine to some power of the same or maybe different argument. So this is going to be the typical example for you. The first obvious step is going to be to make a substitution. U equals 3x minus 2. So that all the trigonometric functions become functions of just one variable u. Then du is 3dx, and you can write that integral in terms of u. Cosine to the fifth of u times sine squared u times 1/3 du. And let me state a general rule here that if all the arguments are the same and linear, you do the substitution like this as a first step. If all the arguments are the same and linear, then do the substitution. U equals that argument. And after that, you are left with an integral that involves powers of cosine and sine. And then the general step there, the general idea is to do the substitution. So let me start over with an integral of cosine to the power of 5 of x, and I will just switch to the variable x, times sine to the power 2 of x dx. Once you have integral like this, you try a substitution again. And that substitution is very simple. It's either u equals sine of x or u equals cosine of x. And I will do both substitution. I will try both for this one. And only one will work. And then we will analyze what is it exactly that makes it work and what is it exactly that makes the other one not work. Okay? So let me do u equals sine x first. Then du is cosine x dx. And then what happens is that to make du I need cosine x times dx. And if I rewrite the integral as cosine to the fourth times sine squared times that extra cosine, then I'm making this du, and I'm left with a product of powers of sine and cosine, and it's easy to deal with the sine, right? It will be simply u squared. Now, what can I do with the cosine? Well, I can use trigonometric identity, right? So this is the identity everybody has to remember and use appropriately. Sine squared x plus cosine squared x equals 1. And from there, you can solve for cosine squared. Right? From there, cosine squared x is 1 minus sine squared. So cosine squared is 1 minus u squared. And since I have cosine to the power 4, I just have to square all that to get cosine to the power 4. And my integral becomes 1 minus u squared squared times u squared du. And the result of that is I'm getting the integrand having no trigonometric functions involved. And that is a very simple integral that you can just expand everything and then simplify. So let me expand quickly. It's 1 minus 2u squared plus u to the fourth times u squared. And that is u squared minus 2u to the fourth plus u to the sixth. And then I will not finish it now, but the rest is very simple. And of course you remember to substitute sine x instead of u at the very end. So this was a success. This substitution was successful in this example. Let me try a different substitution for the same example. So these are the identities, and I'm still doing the same integral. But proceeding with u equals cosine x, then du is negative sine x dx, and to make that du I have to separate one of those signs. And that sign together with dx makes du. And what I have left is again in terms of cosine and sine. And cosine is easy to deal with. It's u to the power 5. Now the problem here is that sine is in the power 1. And that means if I want to solve for sine in terms of cosine, I will have to use a square root. It will be square root of 1 minus cosine squared. And the result here is not as simple as what we had before. Although this integral can be easy to take, for other powers it may not be so easy to take. So in this case, substitution u equals sine x is much more successful. So let's analyze what is it exactly that makes this substitution work much better than that one. Well, of course, in practice you can try both, and if you make a wrong guess, you can do the other one. But what is it that was important here? So when you make a substitution u equals sine of x, it will be easy to deal with any appearance of sine. It will become u. So the difficult point here is the appearance of cosine. And there are two issues. One is the cosine being present originally, and the other is cosine that you need to make du. Right? So what happens here in the process is that out of all those cosines you had originally, you had to separate one to make du, and then you hope that whatever you have left has what? Even power. That's exactly what makes this successful as opposed to that when we had odd power left. So what it means is that originally that power was good and odd. The odd power is the thing that makes this work. The power of sine is irrelevant, but the power of cosine must be odd. And that makes a general rule. If you have a product like this, and one of the powers is odd, you make a substitution using the other function. If you see sine to some odd power, you use substitution u equals cosine. And if the power is even, then you run exactly into this kind of problem. Okay, so there is not much to remember, to memorize at this point. Right? Very simple substitution. And we will not use any other substitution. We will only try u equals sine or u equals cosine.